Let me test on my pen real quick. All right, excellent. So today we're going to talk about properties of the definite integral. And this is part of a video series for Math 115. As we go through, I'm going to stress a lot of theorems and properties that I think are important. And as I do so, I'm going to make sure to tell you which ones will be tested. But I will include some which won't be tested because there may be some people in this class who may go on to take Math 116. And I feel like it would be useful for them to at least be exposed to these properties. So let's take a look. So for the first one, we have two properties we're looking at. We have some real numbers. A, B, and C are our real numbers. And f is some continuous function. And the first property we have is not something that will be tested. But it says that if we switch the limits of integration, then we create a negative sign. So what do I mean switch the limits of integration? I just mean if I'm going from B to A, then if I switch from going from A to B, then it's the same thing as just adding in a negative sign, like right there. Okay, so again, that won't be tested, but that's probably a good thing to know if you're going to take any more calculus. And before we do sort of a visual example, I'll give you the second property, which is just that if I'm integrating from A to C and then from C to B, and noticeably these C's line up, they're the same number, then that's just going to be the same thing as integrating from A to B, our function again, f of x with respect to x. Okay. So that is the full statement of the first theorem. So I said the first property here was not going to be tested, but the second property here most certainly will be tested. So let's take a look at, we'll go to the side here and see what exactly the intuition behind this property is. So we're saying that we're integrating from A to C, so I'll do some tick marks, and then we're integrating from C to B, and then above this I'm going to draw a function. Maybe it looks like this. So this is a continuous function f, which is what the theorem asks us for. And the theorem says that if I take my integral from A to C, and then my integral from C to B, then that's the same thing as taking the integral from A to B. But intuitively, this makes a lot of sense because we said that the integral is the area under the curve. So getting the area from A to C is just the same as getting this green shaded area here. And then getting the area from C to B is the same as getting this purple shaded area. So getting the integral from A to B is the same thing as getting both areas. So of course we have this property that if we just take the sum, if we break up our interval AB into AC and CB, then we get the same thing as if we just did the integral over the whole interval. Okay, so intuitively this makes sense. All right, so what else do we need to know about the integral? So the integral is linear, and that might be a word that seems sort of odd here because when we usually talk about things being linear, we're talking about lines. But linear just means that when I have two things that are summed inside the integral, or I have a scalar, I can separate the sum and I can pull out the scalar. And we'll see what that looks like rigorously. So I have two continuous functions now, f and g, right? And still we're defined on this interval, a to b, and c is also some constant. So c is some real number, f and g are functions. And then here, my theorem tells me that if I'm summing or subtracting them, then that's the same thing as taking each of their integrals independently over the same interval AB, right? So what this plus minus sign here means is that if I had a plus here, then I would have a plus here. And similarly, if I had a minus here, then I would have a minus here. So it's just saying that these signs agree, okay? The other thing is that we said that if we have a scalar in here, so if we have some real number c, so c could be pi, c could be e, c could be a half, 3/4, minus 10, right? Then we can always pull out our scalar. So in other words, integral of CF is C times the integral of F, again, from A to B, because we're talking about definite integrals. All right, so those are properties that are called linearity of the integral. And again, I don't think these are going to be tested. So not super crucial that you know this, but I think these are very good properties to understand, and especially since we may want to integrate, polynomials, for example. So if you wanted to integrate something like, from 0 to 5, x squared plus x, this property tells you, or maybe even x squared plus 2x, this property tells you that you can separate things, x squared dx, and 0 to 5 again, 2x dx. And then I can do another step and make my life even easier. I can go 0 to 5, x squared dx. And then I can actually bring the 2 out as well. So these are just sort of our first properties of the integral. But it might be easier, instead of to try and think of what this thing would integrate to, it might be easier to split it up and think of these things. So that's the power of linearity of the integral. Okay. So what else is going on here? Well, we have a lot of this. This I think is probably one of the more useful theorems in this section, especially conceptually. So let's read through the theorem first, and then I'll show you again another picture that hopefully illustrates it. So here we have a graph f of x, and it's lying above another graph, so g of x. So f of x is above g of x on AB. Okay. Then we say that the area between the curves is the integral of the difference of the functions. So we just said that by linearity of the integral, that's also the same thing as f of x dx minus AB, g of x dx. So I gave myself this little note here to draw a picture, because I think that's, again, the best way to illustrate why this property is true. So let's draw our coordinate axes. And then I have some function f, which is lying above some other function g, which maybe looks like that. And they're both living on the same interval, a to b. Okay. And the claim of the theorem was that the area between the functions is the same as the difference, the integral of the difference. So the area between the functions is this area here, which I will do in red. And we claimed that this area here between the functions is the same thing as the integral of the difference. But we also said that by linearity, that's the same thing as saying the difference of the integrals of each function. Okay. So the first integral, integral of f of x, that's this whole purple area here. And then what I'm saying is, if I subtract off everything below this green line here, which I'm doing in like a diagonal purple, if I subtract off everything below that, then of course I'm just left with the area that was in red. So from this picture, hopefully it makes a little more sense. Okay. So let's see an example of this so that we can start to solve. So we want to find the area between the curves y equals x and y equals x squared. And we're going to say it's between the two intersection points. So the first thing I like to do is, if it's possible, I want to draw a graph of this. So I have the line y equals x. This is y equals x. And then I also have the graph y equals x squared, which I know looks something like this. Okay. So I can determine from this picture alone, before I do any math, I can just determine from this picture that it looks like I probably have two intersection points. One's here and one's over here. So the question is asking me, can I find this blue area between the two curves? So in order to do that, I want to find my bounds of integration first, which means I want to find out where those blue points are. So the best way to do that is to remember that two curves intersect, like two curves y equals intersect when we set them equal to each other and we can solve for that x value. So we have y equals x and y equals x squared. So if the y's are the same, then that means x is x squared. Okay. But x is x squared when x squared minus x is 0. So we're setting this to be true. And then we're solving for the x that make this true. We can factor this. So we get x times x minus 1 is 0. So that happens when x is 0 and x is 1. Okay. So sort of reading from left to right here, I noticed that this left blue point is where x is 0, and this right blue point is x is 1. So if I want these in coordinates, it would be the coordinate 0, 0, the origin, and the coordinate 1, 1. 1, 1. Okay, so the previous theorem told us that if we want this area between the curves, we can take the integral of the difference of the curves. So let's do that. So the integral we just decided was going from 0 to 1 because we're starting at x equals 0 and we're ending at x equals 1. And then we have to take the curve on top and subtract the curve on bottom. So here the curve on top, so if I'm sort of looking in this direction of the purple arrow, the curve on top is y equals x, right? So I put x, and then the curve on bottom is x squared, so x minus x squared, and then we said with respect to x, okay? And now I might want to make my life a little bit easier and separate these things, use the linearity of the integral that we talked about before. So I get the integral of x dx minus integral of x squared dx, both again from 0 to 1. But then we can do the anti-power rule, and we see that the first integral is x squared over 2 from 0 to 1 minus x cubed over 3 evaluated from 0 to 1. So that's the big bar line that I use, means evaluated. And when we do that, that means we have to take the first input minus the second input, so 0, and then minus, and we do the same thing again, the first input, cubed, minus the second input, which is again just 0. So if I work this out a little bit more, I see that the first term is just 1/2, and then I'm subtracting off a third. And if I do some quick algebra, I see that that's just 1/6. So what's kind of cool here is that I get a nice neat number, 1/6, in order to find out what this blue area actually is. Okay. So that's all I wanted to say about the area between two curves, just as an example. And let's see. So most of the work here, I also do want to mention, most of the work here is really done in setting up the integral. So the most helpful thing for that was drawing this graph to sort of see where everything was lying on the plane. And then also I had to do a little bit of algebra right here in order to figure out what the bounds of integration should be. So remember, I set x equal to x squared. Okay. So that's just a recap. Here's two more properties that will not be tested, but I think are very useful all in all. So remember, we talked about even and odd functions very early in the semester, and even functions are functions with a certain kind of symmetry, right? So symmetry over the y-axis. And odd functions are sometimes called as functions with symmetry about the origin, but we can express both of these things mathematically. So I'll write even here, odd here. And mathematically, we would say f is even when f of minus x is f of x, and that's for all x, right? So for every single x, if this is true, then we say f is even. Similarly, if f of minus x, this is just to jog your memory, you might already know this, if f of minus x is minus f of x for all x, so again, on the left side with even, we didn't have this minus. For the odd, we have the minus. Then we say that the function is odd. Okay? All right. So this is a neat thing because if I draw, maybe again, I'll draw another neat graph for my even function. It looks maybe like this. If I'm integrating my even function over an interval, which is also symmetric, so it's minus a to a, so it's the same length on either side of the origin, minus a to a, then I have a neat property, which is going to say that really I could just have taken 2 times the interval, or 2 times the integral from 0 to a. So in other words, instead of trying to worry about this whole interval that I drew in this picture up here, I could have just been worrying about the shorter interval going from 0 to a, 2 times that of the same function. And that's precisely because it's even, because if you notice, the picture over here is the exact same as the picture over here because it's even, right? Because it has this symmetry. And so the areas are going to be the same. And that's why I can just say, okay, double it and have the interval. Okay? On the other hand, if we're odd, then I have an even nicer result, which is that because when we integrate, we count the area with sign. So I'll draw my odd function again. My area over here from minus a is the same size as the area over here to a, but the green area is counted with a minus sign and the purple area is counted with a plus sign. So instead here I had, you know, in the even case I had green plus purple. Now I have purple minus green, right? And that means that because these are the same size and they're counted with opposite sign, we should get a 0 here. So that's the power of even and odd functions under the integral. And I'll stress again that this is not something that will explicitly be tested, but is a useful thing to know for calculus in general. Okay. What else do we need to know? Well, comparison of functions is extremely useful, especially in later brands of calculus. So let's take a look at this theorem. We have 2 continuous functions, f and g. And f is also nice in a certain way that it's between this little m and this large m, and I'll draw a picture for you in a moment that explains this property. So it's between little m and large m everywhere on this interval. Well, then the value of its integral, the value of the area under the curve, is going to be bounded above by the large m times the length of the interval and bounded below by the little m times the length of the interval. So again, this is a property I think makes a lot more sense when you draw a picture. So let's give in a coordinate axis. And we have a and b. And I'll draw a function f. So maybe something like that. And we're saying that if f is below some large m and it is above, whoops, it's supposed to be a straight line, above some small m, then the actual area under the curve is bounded by the area of the rectangle. So here I'll do the large m area is this purple rectangle here that I'm drawing. So that includes, it should include the endpoint there. So that includes everything under the green curve, right? You can just see that visually. So naturally, this large rectangle is going to be bigger than whatever this value under the green curve is. Okay. But then we also have this little blue line under everything, and the little blue line has only this area under it. Okay. So notice that the area, the blue rectangle, is entirely included in the green area, which is entirely included in the purple rectangle. So visually, this makes a lot of sense, but this is precisely what we're saying in this theorem. We're saying that this little blue area is smaller than whatever this green area is smaller than whatever this purple area is. So that's all this theorem is saying. Okay. Well, you might ask, sort of the natural thing is like, what if I don't have, necessarily a straight line that I'm bounded by? What if I have another function? Well, that's a good thing to ask. And also, it does behave in the way that you expect, which is that if some function g is larger than f at every value in your interval, then the area under f is bounded above by the area under g on that interval. So again, this sort of just makes perfect sense visually, where if I draw this picture, I can have some function f, and then if I have, some function g, then this green area that I get under the green curve, so I'll write g there just to remind you, and f here. This green area is definitely going to encompass this black area under the curve f. Okay? So that's all that's saying. And the less than or equal to is just saying that we have this inclusion of the areas. Okay? All right. So this is the last thing that I wanted to stress, and I think that this is something that will absolutely be tested. So this is a little different from the other kinds of theorems we've been doing. Most of them have sort of been just nice properties that we would hope the integral to have, but maybe we didn't start investigating the integral to talk about average value, but it is sort of a nice thing that occurs naturally, so let's take a look at it. So we're saying that the average value of our function on the interval where it's defined is actually the integral of the function on that interval divided by the length of the interval. So if you remember, maybe from statistics or something, there's a formula for the mean of like a set of data. And the mean of your set of data is like 1 over n times, and then you have like a sum, all your points in your data set, say xi, and your mean of your data is this average, right? This is the formula for an average of data. But in the above equation, we have sort of like discrete points that have weight. But down here, we have a continuous function f. And so instead of summing, we're taking an integral. And instead of having the number of data points that we have the length of the interval that we have. So that's sort of the intuition behind this. It's not as strong of an intuition, granted, as some of the visual things that we drew earlier, but hopefully this jogs your memory. Okay, so let's do an example of how I might calculate this just to see that. So I'll do an example off to the right here. So let's say maybe we want to compute the average value of like pi 4/3 pi x cubed, right, over the interval, I don't know, maybe 0 to 2. Okay. So in order to set this up, I first have to notice how long my interval is. So my interval is length 2. So I have 1/2 that I'm dividing by on the outside. And then the bounds of my integration are, again, just whatever my interval was, so 0 to 2. And then if I try to integrate this thing, it might be easier to use linearity of the integral to bring out all these constants. So this is the value that I'm trying to find. And interestingly enough, I know that, you know, the average value of this function is just this quantity. So all I have to do is just some quick calculus. So I'm going to bring out the pi over 3, which gives me pi over 6 times the integral 0 to 2 4 x to the third dx. And the reason I did that is because I already know that by the anti-power rule, I will get x to the 4th over 4 integrating x to the third. And so if I multiply that by 4, I would just get x to the 4th, which is a little bit neater. So I get pi over 6. And then I get, just like I said, x to the 4th, evaluated from 0 to 2. So then I have to leave my pi over 6 on the outside, and then I have to evaluate x to the 4th at each input. So 2 to the 4th is 16, right, minus 0. So my final answer is 16 pi over 6, which I can simplify to just 8 pi over 3. Okay. So hopefully that gives you a little bit of an example of how to deal with these things. And I do have one more example, which I won't go over because it's just odd functions. All right, hopefully that was helpful. And if there are any questions, you can also shoot me an email or any concerns about the lecture at ezel@umich.edu.